Yeah, boy.
Slides where I got hungry. I'm hungry again.
Do you remember that slide?
Yeah.
Already.
My stomach.
That slide has been introduced by you by starting from the extremely very basic equation that is the relationship of the second Snell law between the angle of basically incidence and the angle of transmission across the different two layers. Now, after I strictly basically use that kind of relationship, and I start to build up a trigonometrical relationship between the ray respecting this kind of law and boundary condition. The second boundary condition that I try to respect, because that's the physics that is telling me, is that one, that the angle of incidence is equal to the angle of a reflection. So once you know that law and that law, incidence, reflection, incident, transmission. Okay? Then the rest is all about trigonometry, because the rest I just rewrite the definition of the tangent. The sinus of the angle in bed, cosinus of angle in bed. And I show you that you can write your tangent not anymore in angle, but proportional to the velocity and the ray tracing parameter by using that relationship. The sinus of beta is the ray tracing multiplied the velocity 1. So every time I see a sinus of beta, I do a substitution into that, and that's what I got. So I can rewrite perfectly any angular relationship between the incident angle and the reflection angle or the transmitted angle using a pure velocity and ray tracing parameter. Now, where the geometry come from? The geometry comes from on the equation the x, that is the distance. That one. And the distance is pure trigonometry. There is nothing to memorize actually, because you got the total amount of the distance is basically the bits what I want to do, I want to express that bit of the distance. Well, let's start from the fundamental aspect. We know that the sinus of the angle, so the angle of incidence and angle of reflection, are equal. So all this implies that all the problem can be solved by just taking into account half of the path and then multiplied it by 2 when I got the solution for half of the path. And that is the symmetrical aspect of the Snell law. As soon as that angle is equal to that angle, there's no point to lose all the time to calculate across all of it. Okay? But it's not necessary, because you can calculate for half of it and then multiply by 2, and then you work out all the rest. So that's the first aspect of it. The second, I can express all that distance in there, so say that I can express all that half of the distance between the source and the receiver by adding the piece that is coming from the first incident angle there and the second piece that is coming from the transmitted one is going to be reflecting on the second layer. So that distance and that distance. That one. Oh, that one is nothing else than the tangent of beta is nothing else than basically my bit of my x divided by the thickness. Okay? So I work out that my x is nothing else than the bits that I call h1 multiply the tangent of beta, and I take it twice because there is a piece in there, and then piece symmetrically disposed in the other side. Now I got the other bit in there, but the other bit in there is nothing else than proportional to that portion in that. It's proportional to 1 because when the ray is arriving and reflecting here, you have two options. Remember that the rays, I'm showing only one path, but in reality what he's doing, the ray, physics is telling me it is reflecting there as well, in addition to the transmitted one. The transmitted one behaves like that. So the transmitted one is traveling all across, still reflecting the second layer, and is the one controlling the distance, the bit that I'm missing in order to have the full distance between the source and the receiver. And this that bit, and that bit now is proportional to the tangent of gamma. Same story, is h2 multiplied the tangent of gamma, multiply 2 because I got that one and that one. I got that one and that one, that one and that one. Here we are. How do you move from that one to that one? Well, the tangent of beta has been expressed in terms of the velocity and velocity square and p. And remember, I expressed my tangent of beta by using the fundamental relationship. So maybe the only equation I'm going to give you, if really you want, is the first Snell law and the second Snell law, that is that one. That's it. I'm not going to give you anything else. You don't need anything else. That one is 2 multiply h1, multiply all that object in there. 2h2 multiply all that object in there that is nothing else than the tangent of beta and tangent of gamma. So I'm using basically the simple trigonometry. I'm rewriting it in different way because you need sometimes to rewrite in different way, to use different parameters, to solve different aspects of the problem depending on what is being given to you. Okay? So honestly, it's the only equation maybe I will give to you in case you got completely in the panic and you don't remember the Snell law is that one. But the rest is just a derivative. The derivative is just geometry. It's like a computer machine. You go through it.
Can I ask you?
Yeah.
Can you put the basic geometry rules in for those of us who are not quite to get them? I know them, but.
For your information, yeah.
I mean, in the exam, because then we can derive it from there.
Well, I'm not going to put the sinus or the cosinus the time at the exam because then the external reviewer is going to ask me, oh man, what's wrong with me? Okay? So that's the basics of the sinus and cosinus, and that's it. So it's trigonometry. I'm not going to put any trigonometry on the exam. That's what you need. So, and I'm using, literally, I'm only using those kind of things. The times, if you want to express the times, the time is exactly the distance of basically done by your ray tracing, Sm plus mp, divided by velocity, because space divided by velocity is the time, so I rewrite in function of the time, and my Sm is nothing else, can be written nothing else, function again of trigonometrical parameter, so trigonometrical parameter, because Sm, I can calculate it basically easily by doing the cosine basically of beta is nothing else than basically the piece in there divided by hypotenuse. Okay? Or you can use the sine if you want to use the sine. You do what you want basically, but still trigonometry main aspect. Okay? So I'm keep reusing the same principle, trigonometry and relationship between that one, to write that one, and to reshape that one from angle to velocity, velocity to angle. Honestly, once you play a little bit with that, you will work out basically that you can find your own way.
Sorry, what are S and M and P? Like, what are they lengths? Are they?
X.
So it's just the line SM is the length of it, or?
SM is the length of the ray trace path. Yeah. Okay, it's the real path of the. Okay. Now, that part is what's happening in the case of a dipping layer. There won't be any exercise on that side of it, otherwise you get, because you will need to learn an additional trigonometrical equation, and I don't want to put overburden. But what I want to show you, in a quite possibly rigorous way, is what's happening. You have a dipping layer, and what are the problem of ray tracing in a dipping layer. So, and this is going to be important when I'm going to introduce you the concept of the normal move out. It is a way of simply of reconstructing the geometry of a perfectly parallel layering that we're never going to work out as soon as we have a dipping layer because of that. Now, the first problem you got if you have a dipping layer is that once you are positioning your receiver and your source, in that case is a common source representation of it, So first thing you have to notice, this is a common source representation of the imaging, of the acquisition, because we got a source surrounded by receiver. And this is important because I will show you in the next, probably tomorrow, that the equation written, the only way to write the equation of a deep layering properly is using this kind of representation, the common source. If you do the common midpoint, you have to simplify, approximate the equation, and most of the case you do tremendous approximation problem. So when you deal with deep, basically layering, you need to choose a representation of source and receiver as a common source, basically representation. A source with a series of receiver on the left and on the right. Now, what are those graphics there? Those graffiti. The source. The first thing when you got a deep in layer is that you cannot expect to have a perfectly orthogonal reflection all over the deep in layer. Every source, so that source placed in there, have a perfect reflection, only one point across the full deep in layer, because as soon as you are moving any kind of ray away from this kind of angle, any kind of ray in that case is going to have a path, but it's an asymmetrical path. It's not symmetrical anymore, because the reflection in there is going to be reflected on the path away from there. As it's deepening in that direction, it's going to do, the more it's going to be reflecting along the surface, along the deepening, the more it's going to be longer path to come back to the receiver. So in that case, the property of symmetry are very hard to preserve graphically, because every time you count reflect an object on the both sides is losing symmetry because of the dipping nature of the reflector. So that's make it a little bit more complicated. That means that you need a little bit more information about that. Now, the only way you can solve that kind of problem is by using a kind of relationship that is this trigonometrical relationship that you have to take it as it is, that is telling you, well, you can get there through the basics of the trigonometry. It might take a little bit of time, so I'm not going to spend time on these kind of things now. But this is the relationship that is telling you that SR is basically the distance between the source and the receiver, can be written in terms of the distance between the source and the reflected point, assuming that the ray trace is perfectly orthogonal. So that's basically ray trace is perfectly orthogonal. This is 90 degrees. Okay? 90 degrees. It's 90 degrees in there, it's 90 degrees in there, because when it is orthogonal, it's orthogonal on the both sides. Okay? The S prime is the projection at the exact same distance of the S toward the point of reflection. On the other side, mirrored with respect to the surface. So you represent my two-way travel times. My SS prime is my two-way travel time. That's H and that's H. Okay? SR2, okay, is the distance between that one, the source, and the receiver. And S prime R2 is the distance of the imaginary source, taking into account the real two-way travel times, to the receiver. What is telling that formula is the distance between S prime and R2 is nothing else than the square of the distance between S prime, that is, if you want, the two-way travel path of an orthogonal ray tracing across the deepening surface, plus the distance source receiver square minus the combined multiplication between SS prime and SR2. So there is still a symmetry in this equation. So you are playing basically with those two, basically latum. That one and that one are the game changer on the equation. So you use that one square, plus that one square, plus that one multiplied by that one, by the cosinus of the angle between the SS prime and SR2. Now, how do we, the real problem in this equation, how do we connect that angle to the angle phi of the dipping layer? That's the real fussy aspect of it. Okay, it's quite annoying. Because you got a kind of relationship in which that one is normal to that one. You know that that is 90 degrees. Well, the first information we got is that this is a flat surface, and the summation of the angle around the flat surface is 180 degrees. That's always true. Okay, surface, you got 180 degrees. We know that my gamma here, 180 degrees minus my gamma, is the what it rests of this little bit of piece. Okay, so 180 minus gamma is nothing like that piece. Now, I need to express that piece in a kind of clever way in order to convince you that it's possible to express that angle gamma in function of my angle phi. Now, that angle in there, it's an angle of a triangle that is that one, SO. You go a certain point to basically connect to the surface somewhere here, and the point of the connection somewhere here to my S. Okay, 90 degrees. That angle is the angle of the dipping, so that triangle will have the same dipping orientation than that one. Okay? Because you have a line cut by two parallel surfaces. The two parallel surfaces got exactly the same angle. This is the dipping angle. So if it is true, I know that that portion in there, I can express it as 180 degrees minus the 90 plus, basically minus, if you want, the angle of the dipping. And that is going to give me that component in there. So I'm telling you that this is 90 degrees. This is phi, is going to be the angle of the triangle there, is the angle here is phi. So 180 degrees minus 90 degrees plus the phi angle is nothing else than the piece, the third angle that I don't have. But that one we know is 180 minus gamma, so gamma is nothing else than 90 degrees plus phi. So I can rewrite my gamma here as a 90 degrees plus phi. But the cosinus of 90 degrees plus phi is nothing else than my sinus of phi. That's, I'm using pure trigonometry. Okay? So you can rewrite this equation as cosinus of gamma in terms of sinus of phi. So that's what we want, because what we want to express basically the distance of the two-way travel paths as prime R2 as function of the orthogonal trace, so the zero offset trace respect to that point in the dipping surface plus the distance source receiver, the multiplication of the two multiplied by the sinus of the dipping. Now, let me re-express this old variable with the real physical variable. So, S prime R2 is literally the time that is taking any sort of ray to do something like that and back there. That is exactly the distance between that one and that one. So what I got is the velocity square multiplied by the time square. The time is the one measured by the geophone when it arrived, and the velocity is the velocity that I'm assuming is a constant velocity all through my deepen and thickener layer. One velocity, so it's easy. SS prime is twice the thickness taken at the point O. That is the thickness at the orthogonal basically reflection of it. So it's my H square. As it is squared, my 2H, that is my 2H basically, it is my SS prime, is a 2H, H plus H, it is square, 2H square, 4H square. Okay? Plus the distance between the source and receiver is X square. Is the distance between the source and the receiver. Then I got twice my 2H, SS prime, multiply X, multiply the sinus of the angle of the dipping layer. So, what is telling me? I rewrite, I put the velocity now dividing everything because I want to express the two-way travel time registered by any geophone placed in an experiment in which we are exploring a deep-in layer. Good. Four h squared divided by the velocity is nothing else than my two-way travel time orthogonal with an orthogonal reflection, my tau 0. Plus the components of the x squared divided by velocity squared that come from that one, plus twice 4h divided by velocity squared is twice the velocity as is the time of two-way travel time 0 offset, multiply x, multiply the sinus divided by the velocity. What is telling us, roughly, that equation is that, respect to the classic equation that we should expect to have in case of a perfect parallel layer, we got an additional component, and the additional component is proportional to the angle of dipping and inversely the proportional to the velocity. So what this is telling us that if I know the thickness of a layer at a place, because for example I have a 0 offset information, but I don't know if that layer at the reflection point of my 0 offset is dipping or not, the only way to track it is try to compare which is the two-way travel time arrived at the geophone and which one is better matching, if that formula or the formula of the perfect parallel layer. Okay? So it's telling you that for a dipping layer, you got a little more complexity because any time you are going to reflect produce a reflection, the reflection is going to be completely asymmetrical. The more you go far, the more is asymmetrical the layer. And the more you want to push the angle in that direction, the more it's going to be far, far, far away. So it's pretty much more complicated to trace out the reality of a dipping layer. So you can understand now why, as soon as you got a dipping layer, doing the calculation by hand is not really an easy thing to do. That's why the people try to work out software in which you do the input of that equation and you try to see if the best fit between the two-way travel time and any geophone is fitting that equation or the classical equation that we have seen in the previous exercise. Okay? That one. So those equations that were valid for a perfectly parallel layering, as soon as you enter in a dipping layering, there is the angle component that is basically introducing you an asymmetry and an extra component of in the equation that is not anymore a square equation, but it's a square equation plus a sinus component of it. So now you understand that what we are doing now, we are tracing an ideal ray as we should expect him to come back to the geophone. And when we do a migration is an exercise in which we compare the two-way travel time registered by a geophone with a kind of model equation in which we try to understand if that two-way travel time fits with a perfectly parallel layer or with a kind of dipping layer. And that's the first step in which you start to do a proper kind of simple migration modeling. Try to understand if the geometry of your stratigraphy, is it dipping or is it perfectly parallel? You need to use those equations. Well, you know some parameter on those equations because you can work out the 0 offset, that is where you got the source and the receiver in that place. You have to put the receiver in that place and work out tau 0. That is the place where you got the perfectly orthogonal reflection. That is the minimum distance. So the first basically impulsive information that you got at the source and the receiver, 0 offset, is going to be exactly that one by definition. So you know that. You can measure that. X is the distance between the source and the receiver, and you can control it. You can decide it, so you know it. The only thing you cannot work out, tau 0 is still the same, tau 0, the only thing you cannot work out is the velocity and the angle of the dipping layer. So you got two variables in there that are hardly solvable unless you start to put a series of equations with a relationship between the angle and the velocity. Now, in case of a dipping layer, the experiment of using a direct wave, that you know it's a kind of 80, 90, 70%, whatever it is, proportion of the p wave can still be done for the first layer. So if you don't know the velocity in there, but you got the direct wave arriving there, the direct wave is still a proper wave that you can still use even for a dipping layer. So for the first layer, you can still get that velocity. Now, the only thing you have to calculate is by using the two-way travel time that is measured at the geophone, you can work out which is basically, you know that, you can work out which is the angle of the dipping layer. And in theory, if everything is alright, you should expect to have, for a certain angle that are an angle between 0 and 90 degrees, so in one direction, then the velocity of arrival on a two-way travel time is going to take a little bit longer respect to a perfectly parallel condition. So if you think that your geometry, so if you still don't know which is the dipping geometry of the layer, you start to get some two-way travel arrival that doesn't match the equation that we have been playing up today, so the equation in a perfectly parallel scenario, well, and it's taking a little bit longer. It's telling you that the dipping direction is along the direction where you are measuring, and it's producing a reflection wave that are constantly delayed. If the constant delay best fit with the constant angle of dipping, you can work out the dipping of your layer. Okay? The problem is that if you go on the other way, it's the complete way around. Because the other way, basically the reflection, they are doing shorter and shorter and shorter path. So the more you're putting the receiver on the other side, the more you are breaking the symmetry. So if it was perfectly parallel, the receiver on the both sides should have measured exactly the same two-way travel time for the exact same offset. As soon as you're putting a dipping, no way. The one on the left side, so on the direction of the growing dipping, is going to measure faster and faster and faster and faster two-way travel times. So you start to have a two-way travel time arrival at your geophone that is extremely asymmetrical, and that is the first clear signal that you got a dipping geometry below you. So coming back to the boundary condition of the system, the best way to test if you got a dipping geometry is to use a common source geophone geometry. Because with a common source geometry, you can track immediately if the symmetry of the two-way travel time arrival for geophone that does exactly the same offset on both sides are identical or not. If they are not identical, then there is a dipping orientation. You still don't know, but you know it's dipping. Okay? So that's an important constant. So I won't ask you to write me the equation. If you want to write me the equation, you have very good champagne. That's not a requirement, but I want you to understand the physics behind that. So if I ask you a question, the second part of the exam, much more theoretically, we ask you which are or you can track if a layer is dipping or not, which kind of acquisition design you have to plan, common source, and which kind of two-way travel time data you have to compare, as the two-way travel time data compare respect to one side or the other side of the geophone. Okay? They are perfect, they are completely asymmetrical. Is it clear? Good. Now, up to now, I've been introducing you the ray as a kind of ray that are perfectly respecting the Snell law, so they are reflecting in such a way that if you are in a parallel system, angular incidence, angular reflection is still valid. It's still valid on the dipping geometry, but it's much more hard to find which is exactly the place where you have to put the geophone in order to track the symmetrical one, because the dipping is producing an asymmetrical geometry. But we got an extra ray, basically, that is complicating our life. But it's the joy of all the exploration geologists, because it's the joy of the people that use the refraction. We know that from the physics and from the Snell law that if that principle is correct, so the sinus of incident ray divided by velocity 1 is equal to the sinus, leave it the 90 now, but the sinus to the transmitted ray divided by d2, we know that there is an angle where the sinus got a value exactly 1. And the angle where the sine has got a value exactly equal to 1 is the angle that's called critical angle, in which the ray tracing stops to reflect, but it refracts. So it decides to move exactly at 90 degrees. At the 90 degree, if the way we are measuring our angle of incidence, if this is basically 0, this is the 90 degrees. So it's the angle in which my ray tracing starts to behave as a head wave and travel along the discontinuity, and it travels along the discontinuity following that principle that the sinus of the critical angle is equal to the velocity 1 divided velocity 2. That's important, because that's introduce you the physics of the special type of ray tracing, that is the refraction ray tracing. So, if you want to calculate basically your critical angle, you do the arc sinus or the inverse of the sinus, V1 over V2, and you got your critical angle. Okay? Easy peasy.
No, sorry, no.
Just do an operation of a kind of algorithm operation. So I want to calculate my angle critical. You do the arc sine or the inverse of the sine. Okay?
Okay, yeah.
That's it.
That's I minus 1. Like, I don't know what arc is.
Yeah, it's sine.
Oh, it's the inverse of the sine. I don't know. You want to arc? It's the inverse of the sine. Well, you have to invert the function. I want to get my e basically. Okay. So I move on. Now, what is the problem with the story behind the refraction? The problem we got with the refraction is that there are something strange things happening there. Because the first things we have is that when our ray tracing is becoming a refraction ray tracing, it decides to travel along the highest velocity layer, not along the lower velocity layer. Because when it's traveling along the discontinuity, you have two options. You have the option of traveling along the discontinuity at the velocity of the lower layer, the one on the top, or better, not lower layer, at the velocity of the layer on the top, or at the velocity of the layer below. So that's the option he got. So the ray travel along the interface. What layer is each? Ray aren't real. That's the other problem. The simplification I'm doing, as I told you the first lecture when I introduced the ray tracing, is that a geometrical simplification in order to get right the relationship between reflection, transmission, etc. Now we know from the physics of the first lecture that any sort of P wave is a kind of P wave in which you got the spherical spreading of the energy. So now we have to combine this kind of two way of thinking or behaving of the wave in such a way that we can explain the refraction wave. Because the refraction wave by itself, the ray tracer doesn't explain. It doesn't tell you the Snell law if it is traveling there and there. Still not. Well, we show it kind of tell you, but it doesn't help you to understand why after a certain steps and a certain while, the refraction wave decide to come back to the initial source. So, the first thing we know, and we know from the Snell law, is that in order to have a refraction, we need to have two layers with different velocity. V1 and V2, because if V1 is equal to V2, it's never going to have a critical angle. Because the ratio is 1, so the ratio between sinus of the angle and the sinus of the reflected angle is basically equal to 1. But this implies that I don't have any transmission, because the two have the same velocity, so it just doesn't see the two lithology. It sees the two lithology as a single one because the same velocity. So Snell law is still about velocity again. Now, the reality is that if you want to explain physically the refraction, you have to look at with this kind of gentleman, Huygens. And Huygens was a kind of Dutch guy that was basically studying the at the time the equation and try to understand how they were behaving. And you realize by observing the normal system that as soon as you got a drop into the water, or a piece of rocks into the water, the game you do when you are young, to see how it looks like, it starts to produce a series of basically pressure, perfectly horizontal, that are perfectly coherent and consistent with the P wave pressure propagation, the spherical spreading. So each point is Huygens start to basically describe the diffraction, the diffraction in a slightly different way in respect to the Snell. He wasn't thinking about any sort of ray as linear ray, but he was thinking basically the ray as wavefront, in which every time you got a P wave that is basically reflecting any surface, that surface becomes the producer of a new P wave. So any potential reflector becomes a source. So you start to describe as a wavelength, as each point along a material that acts like a point source of wave. So every time you basically shoot a P wave across a reflection, it does the same effect as when you basically throw out a piece of rocks into the water. It creates through the surface and you say it's a waves. So what you got is that every time you got a wavefront, and wavefront is kicking basically a surface, planar surface, it starts to produce, starting from the center, because it's where the wavefront is basically touching first on the radius that is nearby the basically the surface, and then laterally you got all the rest of the front that is touching basically the rest of the surface, and the rest of the surface start to vibrate and start to produce new waves. So every potential reflector becomes a source. And that's a way of conserving basically the reflection properties. And every time you got a new wavefront, you got the wavefront is pushing over, reflecting a surface, creating this kind of potential new source, but this kind of potential basically new source, they behave following basically the principle of the geometry. So if they are perfectly in a line, so perfectly if you want in the space front of view in phase, they produce the same amount, and the wavefront is a single wavefront that is kicking that surface. It produces a series of an infinite source, producing a series basically of new wavefront, every of them same property in terms of velocity, of energy, etc. So they have exactly the same radius. So that's the way you can reconstruct your new wavefront. And here you go, you kick another surface, you reproduce another series of basically wave, new production of wave. One front, one velocity, doesn't mean that you get only one kind of spherical spreading wave, all with the same radius, perfectly in phase. And then that's the way you reconstruct the wavefront. And you can keep going on at whatever frequency you want, at whatever dimension you want. That's the way that the people that Huygens start to see and to think any sort of reflection and propagation of the P wave. And you continue like that, new wavefront, final front, the more it's moving out, the more the spherical spreading becomes important, so the more the density of energy across the surface becomes lower and lower, but the more the circle, basically, the kicking the new surface becomes bigger and bigger. So the more they interfere with other surface, and your new final wavefront, again, if it is propagating to a medium that has a single velocity, same radius, same story, you keep moving on. What's happened? Why the people, decide at a certain point to move that way? Snell was so simple, so clear. Why do we want to use this Huygens way of explaining the wave? Well, because that's the place where the Snell theory of the ray tracing doesn't work. And it's the physics that is telling us it doesn't work.
Do the waves not cancel each other out?
Pardon?
Do the waves cancel each other out?
If they are not in phase, yes. But if you are using a ray tracing, that's what the ray tracing theory is telling you. The ray tracing theory is telling you that what you got is that if you got a little bit of space in which you can penetrate basically all your ray tracing, you have a complete basically array of ray tracing, but it's a linear propagation of it. You can arrive at there, and there, and there, but there are places in which the boundary at the extreme side doesn't allow to any ray trace, because they are linear ray trace, to move on. Especially if you are in a medium, like the air, in which you expect to see no transmission, so same velocity, so same properties of refraction, so there is no refraction basically there, air over air, no problem, but that's what the ray tracing is roughly telling you, that there is in a certain space an area in which you can trace the ray. But beyond that, it's very hard to explain using the theory of the ray tracing. If it is true, then if you open the door and I try to speak with someone else on the back of the door, just on the back side, if the ray tracing theory is correct, you should not hear anything. The waves should pass on in front of you. As soon as you are behind basically the wall. And we know that is not true. And the reason why it's not true is because the wave are, we know, pressure wave that propagate as a spherical spreading, and every time they propagate, every time whatever object they are basically interfering with it is reproducing itself new source and new waves. If you reproduce new source and new waves, all the boundary of the very acute boundary become potential source of the wave. The potential source of the wave, the spherical spreading, allow you to hear what you got on the back side of the door. So that model, physical model, in reality, is the most correct, and actually fit very well with the concept of the P-wave propagation across a system. Why people didn't use that? Because mathematically it's a bit more annoying. If you want to write the equation on a system like that, the equation is a little bit more complicated, because you have to write the equation not anymore as a trigonometrical fashion, but you have to write the equation in terms of the P, of the radius, of the wave equation, of the energy, etc., etc. You need to basically write up the original equation I introduced you with the whole component inside. Why? With the ray tracing, most of the reflection and part of the refraction prediction can be described perfectly by their single ray tracing. So for simplicity, people have been using, starting doing the ray tracing in that way. Now, so basically what's happened is that they start to hear each other's, because the front of the wave starts to propagate, and there is any sort of either angular or shadow zone. If it becomes a potential vibrant place interfering with the original wave, it produces a wave, and then you have the front of the wave, and then you can hear laterally pretty much easily. Now, why all this kind of story behind that? Because when you got your wavefront that is arriving as a ray tracing, so that's the Snell ray tracing, and this is the wavefront that you got when you do the experiment. So this is the spherical spreading associated to it, with the density of energy slowing down the more it's propagating, and this is the ray tracing kicking the surface. If it kick at the critical angle, it starts to travel 90 degrees as a refractor, and that's what the Snell law is telling us. What the Huygens law is telling you is that as soon as it's kicking that surface, it starts to produce waves. It starts to produce source of the waves, but it starts to produce wave in couple of waves. Waves in which you got the front of the wave in that direction that is propagated with a certain radius and a certain spherical spreading that is proportional to the V1, and you got a propagation of the second bit of the wavefront below at the layer that has a different velocity, so a different spherical spreading. So the spherical spreading there is different compared to the that one. So what the Huygens theory is telling you is that in reality, when you got a ray that is arriving at a critical angle, it's not true that it's traveling only along the discontinuity, but it's immediately producing sources that are already arriving to the system. Which one is arriving to the geophone? Is the one that is exactly at the wavefront, exactly at the position of the source, is going to be the one that is going to be traced by the receiver. Okay, so you got your source. Now your new source is that one. You have to trace which one of those rays can be traced basically by your receiver. But already when you arrive to the basically angle of reflection, or the point of the reflection, you already produce your source. And you already produce reflection. So what you got? You got a full stream of series of waves or people call wavelet, which the tangent of the front of basically this wavelet, they are called basically head wave. And the head wave, they are produced in both directions with different, basically, spherical spreading, different property, and the property controlled by the V1 over V2. Basically, if you got a geophone there, we are going to track the first wave at a place a certain distance. Now, the head wave that propagate up, so the one that go back, produced by the source in the direction back of the receiver, they are called head wave. And they are basically refracted wave that behave slightly differently in respect to the reflected wave. Okay? Because they are produced by a potential source that is producing a series of waves that are splitting, if you want. One, as a head wave come back, is going to be registered with the receiver. The other one that are propagating below the layer at the velocity that is pertinent of the layer below. There is a boundary condition in that. And the boundary condition is that in order to produce head wave, and that's the experiment that is telling us, the experiment is telling us is adding an additional boundary condition to that. The boundary condition is that the velocity of the lower layer has to be always higher than the velocity of the first layer. If the velocity of the lower layer is lower than the velocity of the top layer, you're never going to get any kind of head wave. So that wave doesn't come back. You never got any head wave back. You produce, the source is producing a kind of spherical spreading waves, but they never go back to the receiver because they got counter-reflected by the one on the top. So, say that to describe the behavior of the ray tracing behavior of the refracted wave, we can still use the Snell law, but now we know that the Snell law stopped to work, or stopped to describe the real physics in between there and there and there, because the Snell law doesn't tell us exactly which is the physical reason why that object at some point come back there. In reality, we know that there is nothing that does exactly that path. This is the way, a simplified way to describe it to solve our problem. But in reality, as soon as it's kicking out something, this kind of refractor, it starts to produce wave, and only the one at a certain distance will be able to track basically the receiver on the top, and only those one characterized by a velocity of the lower layer that is bigger than the velocity on the top layer. So, if you got a cross layer, and below the cross layer you got another object with a partial melting with the velocity is lower, you're never going to have refracted wave. So to have refracted wave, you need to have V1 lower than V2, and V2 is the layer through which the refracted wave is going to propagate. So for a while, the Snell law is telling you that the refracted wave is propagating, if it is produced, along the higher velocity layer. So, now we put all together, we do some trigonometry, something you know very well. Same story, so the problem is that now we got, this is the relationship between the sinus of the critical angle is nothing as the V1 over V2 multiplied the sinus of 90 degrees. We have seen already that, so I do the arccosine. So the phi is the arccosine of V1 over V2. Good. SP. SP is the basically path of my ray at a critical angle before it gets transformed into the refracted wave. Before it gets transformed into the refracted wave, it has a path that can be pretty much described by S prime, this is S prime, okay, there's a projection of my S, divided by what? By the cosinus of my angle, critical angle, in that case is nothing else than that one over that option in there. So my QR, if you want, is nothing else than the projection that my SP, exactly that, is nothing else than my QR on the other way. Because what the Snell law says that whatever is a refracted wave, it comes back with the same critical angle that was moving. So Snell law is still valid. So this is the critical angle. It travels for a while, we still can know. might have to come back even at the critical angle, at the exact same critical angle it was inside it. So Snell law is still valid. Trigonometry. That's a good thing of why do people use the Snell law to describe them, because it still works. SP and QR are nothing else than my SS prime. And my SS prime is nothing else than the thickness, the real thickness, my H, the one I'm looking at, usually when I want to do some experiments. So, all the PQ, so all what it rests, so the difference between that bit and that bit that can be perfectly traced out because you know exactly which is the critical angle, is nothing else than the difference between the distance of the source and the receiver, my X, minus twice 2SP multiply sinus of the critical angle. It's twice basically H, I substitute my SP, my H of the cosinus of the critical angle is the tangent of the critical angle. So it's telling me that my PQ distance is proportional to the tangent of the critical angle. So it stays along the high velocity discontinuity part, or stay along the discontinuity within the high velocity part of it, depending on how much is the value of the critical angle. And the thickness, of course, to get there. Why? Well, but now I have to put all together, because now I can write the equation of the two-way travel time from a ray that is doing that path. That one, and that one. That one is PQ, is nothing else than that one. And that one is the piece, my x minus 2h multiplied my tangent critical angle divided by what? By velocity 2. So the velocity is traveling at the velocity of the highest layer. Remember, if the velocity 2 is not bigger than velocity 1, you are never going to get that ray. It doesn't exist. It doesn't produce. Higgins tell us it doesn't produce any refractive ray. The two pieces in there are nothing else than those pieces, SP and QR, so basically my SP, my QR, twice, and divided by the velocity of what? In that case, along that path is traveling along the velocity 1, that is the lower velocity. So you got a piece traveling along the velocity 1 and a piece traveling along the velocity 2. Now, the only thing I'm doing there, I'm just rewriting the equation by taking basically that, the common basically denominator of those two, okay, and I'm splitting things. Yes, I'm taking the common denominator, taking the cosine of the critical angle. So I take x over v2, that is x over 2, plus 2h divided by cosinus of the critical angle, that is here, so 1 over v1, minus sinus critical angle over v2. Sinus critical angle comes from the tangent, that is sinus over cosinus. And that's my new equation. If you rewrite that equation, so you apply the multiplication of that one, the cosinus of that one, you apply that one in there, and you do the whole algebraical component, what you got is that, or you simply rewrite, for example, the sinus in terms of, the cosinus in terms of the sinus, you got an equation that is like that. Now, wait a minute. Right. What we got is now an equation in which the arc sinus of my velocities is the velocity of the higher velocity low divided by the velocity of lower velocity. My equation is come from, of the cosinus of the critical angle come from that one. Remember? And that one is 1 minus sinus square of critical angle is the cosinus square of the critical angle. Write the equation. If you look at the equation, go to the main parameter. The only way you can have a critical distance, the critical distance is the minimum distance in order to get a refracted, basically, ray. And to get the minimum critical distance is nothing else than that distance that is function of the various critical angle. As you see, it's proportional to the inverse of the root of the square velocity 2 minus 1. If velocity 2 is equal to 1, that story is never going to be possible. So in order to have basically, and velocity 1 has to be always lower than velocity 2, because on the root it doesn't make sense. So it's telling you that equation, that in order to have a refraction, you have to have a velocity 2 that is bigger than velocity 1. Right. It's telling you that in order to produce a refractive angle, you need to wait a certain distance. So all the geophone at the distance below or with the position before that critical angle, they are never going to track any refraction wave. So there are a certain amount of distance that is required in order to see through the geophone the refracted wave that is beyond the critical angle. The critical angle is controlled by the difference on the root of the two velocities, so the bigger is the velocity difference, the more is going to be higher the critical angle, the more is going to be higher the critical distance, the farthest I need to put a geophone. That explains to you a couple of things. Why when you do a refraction experiment, you use very large offset geophone, or you do basically an acquisition in which you got very far offset basically geophone. So usually the refraction is used to track discontinuity at the regional scale, to do a pre-exploration basically gains to understand the regional geology, and you don't need that big basically or large amount if you want of geophone, because the geophone need to have at the minimum distance to track at least beyond the critical distance the main refraction behavior. Okay? Well, then you can work out all the PQ, so the PQ can be written in terms of the tangent and critical angle, the distance between basically the source and your receiver minus twice the thickness multiplied by the tangent of the critical angle define you the distance within which your ray is traveling along the highest velocity, so how long is going to behave as a surface wave if you want. But it's telling you some other interesting things. The critical angle is that one. Okay? The critical distance is proportional to the critical tangent critical angle and is proportional to that properties. As you have a P wave that is traveling for a while along the discontinuity at the velocity of the higher of the lower basically object that has to be at a higher velocity, it implies that depending for how long it travels along the highest velocity, that ray, that head wave, it can in certain cases arrive before the reflected wave, and most of the cases I tell you already, and in some cases even before the direct wave. And you can pretty much understand that because the velocity of the head wave is the one we derive basically from that equation. It tells you that you have basically the distance plus twice the thickness over V2, that is how much time is spending, how much time is doing traveling along the highest basically velocity layer. If you want to know when this kind of refracted wave arrives exactly at the same time of a direct wave, that is that equation, you need to solve that equation. So x prime over V1 is equal to the component that is traveling as a direct wave along the V2 plus twice h over v1 cosine of the c, and what you you do your calculation basically. So you put the v1 and v2 on the other side. You calculate which is the basically the distance at which the direct wave arrive exactly the same velocity, exactly at the same times as the direct wave, and you realize that is depending on the ratio between the summation of the first layer and second layer divided by the difference between the first layer and second layer. So, the bigger the difference between the lower layer, so the high velocity layer, and the first layer, defining the discontinuity, the farthest, the more space need to the refracted wave need to do in order to arrive at the same time of the direct wave, or even before. So in a diagram in which you got offset distance, that is your x, if you want, the distance between source and geophone, a generic distance, but is represented by the distance between the source and the receiver, times, this is the equation of a direct wave. Direct wave, we know, is literally a wave that is traveling along the discontinuity, is a surface wave, and is directly traveling from one point to another point, from the source to the receiver. So the equation is a simple equation of a linear equation, space over velocity. It's a simple one. The equation of my refraction wave is that equation. It is again a linear equation depending on V2 and V1. And it's telling me that in order basically to be produced, I need to basically to start at a critical reflection point, that is that one. Okay. So you need to have a certain amount of distance in order to produce and to see the refracted wave. Remember, that is the critical distance, and it is that one. But once it starts to travel, there is a limit that is called the crossover point, in which the direct wave arrives exactly at the same time as the refracted wave. So at a certain distance, at a certain geophone, you start to see the arrival of the direct wave, the refracted wave, exactly at the same time. Beyond that distance, the diagram is telling you clearly that the refracted wave is always arriving before the direct wave and before the reflected wave. So that diagram, it gives you the general rules of what you should expect to see at the geophone when you are doing an experiment in which you take into account direct wave, surface wave, and refracted wave. We got the equation. We realize how the equation of refracted wave, don't look at that one now, is strongly depending on how long it stays along the higher velocity V2 layer. The longer it stays, the more faster it travels than the direct wave, the more it's going to arrive before than the direct wave. But in order to see that, you need to wait a certain distance. This is the crossover point. So at that distance, the first time arrival is the one of the direct wave. Then you got, probably if you don't have, you don't know, but if you don't have a refracted wave, you got the reflected wave. At that distance, when you start to see the first refracted wave, you still got a kind of certain distance in which you get first the direct wave, and then the refracted wave, and then the reflected wave. So basically, the P-reflected wave is always the last one to be seen in a geophone. And the reason why it's doing that, you can pretty much understand if you remember, which is the tracing path that is doing the reflected wave. It's doing a path that is apart from the one that is exactly at an orthogonal position respect to the layer, so the one at the zero offset, and this is the one at the zero offset. At the zero offset, you got exactly the tau zero, so the reflection intercept times is the time that your ray tracing is doing when it is perfectly orthogonal. So that one is the only one that is giving you the real time thickness of the layer. All the other geophones with a certain offset are measuring the reflected wave, but they are measuring the arrival reflected wave of a reflected wave that has been doing a ray tracing much longer than the real thickness because of the angle of the reflection. And because of the angular equation, the ray trace path, you remember, you wrote the equation that is a Pythagorean equation that is proportional to the distance square plus the thickness square. So as it is a square plus a square component, your equation is an hyperbolic equation. So that's why in a geophone, or in a series of geophones at a certain distance, the reflected wave is represented as an hyperbolic, basically, object. The trace design the arrival of your P wave at various offsets as an hyperbolic wave. I show you what you should expect to see in a geophone, but then tomorrow we will do step by step a kind of simulation of what you expect to see at various geophones at various distance before the basic critical angle and the crossover point, etc. But that's what you expect to see. This is a forward modeling, more forward modeling I did by using very simple parameter in which you got basically a velocity of a layer, and I'm simulating what you expect to see at various traces far from the source distance of the geophone. Those are the traces that you should expect to see in a pre-stack shot gather. First arrival for a certain distance is the direct wave. Point in which the direct wave arrives at the same time the refracted wave is the crossover point. Below that, beyond that, that point, the refracted wave starts to arrive before the direct wave. The farthest is the crossover point, the more the difference between V2 and V1 is bigger. So the more the V2, V1 velocity in order to have a refracted wave are similar, the more the crossover point is going to translate somewhere here. So the more the intersection between the green and the red would be there. The disparate, the real disparate, are the blue one. But the blue one, they are the only one representing the real reflection. Because a reflection in pre-stack shot gather are represented by an hyperbolic series of what? Of series of geophones that are tracking the arriving of the reflected wave at different offset later and later and later on. Because the more they are far, the more the wave have to travel more to get there. So the more is the picture is an hyperbolic picture. Where the problem starts is when those three objects are nearby each other, they are interfering each other. Because the first things that you learn when you are doing an interpretation of a seismic data set is that when you are acquiring seismics, as you only want to see the geometry of the reflection, you don't care about the direct wave, so you want to cancel the direct wave. Look like easy to cancel there. It's not that easy to cancel there, because you cancel that one, you're going to cancel as well the blue one interfering with them. Okay? So, the rest of the course, tomorrow we are going to see how, step by step with a simple simulation, the direct arrival, reflected wave, and refracted wave works. The more you move away from the source, how you can interpret the real pre-stack shot gather. Then, we will apply some of the concept about the velocity for the tuning thickness, frequency, use of the frequency to better visualize the seismics. But the processing, basically, activity of a geophysicist or geologist that is working as processor is to get rid of all these kind of objects, the direct wave and the refracted wave, to preserve at best the reflected wave. As you see, easy peasy if you are here, it's a mess if you are here. We have to learn some other couple of properties of the wave to understand we can play with those. Clear? I think your brain is mucking. But we are going to come back tomorrow to that stuff again. Yes.